Hi, everyone. So a couple of years ago, I attended a functional programming training where we implemented type classes, I think. And I thought I perfectly understood what was going on there. But then the next Monday, I came to my workplace. And if I were to explain this to someone, like what I did during the workshop, I wouldn't be able to do it, because this means that I haven't really understood what I've been doing there. And I haven't had a similar story with monad transformers, because once when working on a project, I hit the wall when writing a for-comprehension. And like the problem appeared to me like something that probably someone has already solved. And it was actually true. So today I want to take you back again on this journey with me. My name is Jacek Kunicki. I work at Software Mill with the Scala consultancy based in Warsaw, Poland, that actually based everywhere in Poland. That's pretty much it about us. Okay, so we're going to start with a probably close to real life example. We have a very simple domain which consists of a user and a company, and they have their IDs and their names. And now what we want to do, what we want to implement in our code is this method. So we have some existing service that is described by the two methods over this one. So we can find the user by ID. We know how to do it. We can find a company by a user. We know how to do it. The implementation details are not relevant at this point. And what we want to do is actually to find a company by user ID and return a company. So this is our problem statement for today. There was already a great keynote about effects by Adam, so I'm going to continue from there. In our case, the effects, so we have a type alias for some kind of an effect that is going to describe what can happen to the object that we are returning. So how the service that we are using that finds the user by ID and finds the company by user, how it can behave. So for a start, we will assume that this service is very simple, and actually our effect is kind of an identity. So this means that find user by ID will just return a user, find company by user will just return a company, nothing more to it. So let's implement this one. In this case, it would be pretty trivial, because this is going to be find company by user, find user by ID, and that's it. So this works. Thank you for your attention. Well, not exactly. Because I told you that we are going to look at quite a real world example. So this is not actually real world, because in the real world, there is a couple of things that might happen, that might go wrong. So the first thing that might happen, and this is what we are going to describe by our first effect, is that the user might be there or might not, because the ID might not be valid. So we are going to replace our effect, the identity effect, with an option. So the first effect we are dealing with is an option, which denotes that the user might exist or not. Of course, our find company by user is not going to compile at this point, because what we are getting here is an option of user, and we expected a user, so we need to deal with it somehow. Fortunately, in Scala, we have a tool that is going to help us with that, because we have two options that we want to chain, so we can use a for-comprehension for that. So we are going to look up the user by ID. Then we are going to look up the company by the user. And then we are going to return the company. And that's great. So this works. The for-comprehension compiles. We are in Scala, so if it compiles, it means that it's going to work. So that's perfect. But we are still a bit closer to the real world, but not too close, because we can assume that we are fetching this user and this company, for example, from a database or from a network call, whatever. So this means that there's going to be another effect involved, which would denote doing something asynchronously. So apart from the option that denotes that the user or company might be there or not, we also need another effect that is going to denote that this is happening like in the background. So we're going to use the built-in Scala future. So now our effect is nested. So we have an option that is nested in a future. So we have two effects describing what can happen. And we can see that our code stopped to compile. There are a couple of reasons to it. Well, first of all, we are doing some transformations on the future. We need a thread pool for that. And this is the way to provide a thread pool in Scala is by providing an execution context. So we are going to provide one. Actually, in this case, it even doesn't have to be named. We just need to assume that there is some execution context in scope that the future transformations can use. But there is another issue to that. So if we look at the error message here, we can see that actually we were expecting a user, but we got an option of user. Why? Well, because we actually, when we tried to access what is wrapped in our effect, we only got like one level inside. So we got only into the future, but we didn't get to an option. What we would like to have here is the user, but we got the option of user. So of course we can handle this here somehow. We can take the user, do the pattern matching on the user. And then when the user is present, we can actually call find company by user by providing the value here. And if it's not, we need to handle this somehow. So we need to return a none, but wrapped in the external effect inside the future. So we're going to use future successful of none for here. Now this is going to work, but our idea when writing for comprehensions, which or you can think of as a tool to chain dependent computations together, our goal would be to have a for comprehension that consists of like simple lines that you write one by one, and like you chain a couple of computations, then you get the result. So what we are doing here, like the pattern matching inside the for comprehension, this is something that we would try to avoid. So let's come back to the previous version of this, which didn't work, and think what we can do here. So perhaps you are aware of the fact that a for comprehension is actually a syntax sugar for a chain of flat maps and then a map. So all the generators or all the arrows except for the last one are flat maps, the last one is a map. So we would like to have for our effect to be a type that we can use directly in our for comprehension. Instead of using the future of option of A, we would like to use some other type that suits the for comprehension somehow. And what does it mean that it suits a for comprehension? Well, looking at this, the sugared code, this means that we need to have a type that implements map and flat map. And then this should be enough for the type to be used in the for comprehension. So let's try to do it. So this is going to be some kind of a wrapper. So this would be a case class. And this is going to hold an option that is nested into a future. So for clear naming, we will call it option inside future. There's a typo here. It's going to have some generic type because we want to hold values of arbitrary type inside. It's going to have some value, which would be, well, a future of an option of A. So actually what is described by our effect at the top. And what we know for now about this case class is that we want to implement two methods. So we want a map method that transforms to some other type B. This takes a function from A to B and returns our type. So returns the option inside future of B. There will be some implementation here for sure. And from the desugaring, you remember we also need a flat map. It's going to look a bit similar. So of course it will be called flat map. And then the function would be a bit different because in flat map, the function that you pass returns a wrapper. So it's going to return the option inside future of B. And that's it. So now if we go back and change our effect here from the nested future of option of A to our option inside future of A, you can see that the compilation error here is gone. So it looks like the class that we created with the API that has not yet been implemented is suitable to be used in a for comprehension because what we are going to get here is actually the user. So it's not an optional user anymore, it's an actual user. So looks great. So the only thing left now is to actually implement the map and flat map methods for the option inside future. So let's do it. So you remember that the issue with the user in the for comprehension was that we had like two boxes. So there was this first box, which was an option, and there was the outer box that was the future. And when we did the flat map, which was the for comprehension, actually we only stepped into the external box. So we stepped into the future, but we actually wanted to step even deeper into the nested box, into the option, and actually apply our function to the value inside. So the double nested value. So what we want to do here, we want to take the value from our wrapper, which is the future. We want to call map on this. And then actually so now we got into the first box, into the future. Now we want to get into the second box, so into the option. So we take the option and we call map on this once again using our function f. And what it does, you can see there's two calls to the map. So this is like double nesting. So we are solving the problem here in the implementation of map of our wrapper. So there is something missing here. Let's see what. Well, again, we are mapping over a future. So we need to provide a thread pool for that and execution context. So let's take it from here. So now we are almost there, but we need to remember that now we are returning a future of option of B, but we need to return our wrapper. Fortunately, our wrapper has an apply method that does the conversion. So we just write option inside future here. And that's it. So we have implemented the map method that covers the double nesting. So it goes to the nested box. So now let's try to implement flat map. We already know that we would need to return the option inside future. So let's start with the wrapper. And probably this is going to be a bit similar, like the approach would be similar to what we did with the map. So we're going to say value, flat map. And then you can see that we are again we need a function that takes an option and returns a future. And actually what's going to happen here is going to be similar to what we initially tried to do in the for-comprehension. So we need to pattern match on this option that was returned. I just call it A, so that it's not confusing with the value in the wrapper. And now we want, if the value in the option was present, we want to apply our function f to this. Which is going to return us a wrapper because it returns option inside future. And here actually we need to write a function that returns a future. So we need to add value to this, so or call value so that it gives us the actual future. And now there is another case when the option was empty, and here we need to return again a value of none wrapped in our future because this requires the future. So we're going to say future successful of none. And we still need an execution context because we are flat mapping on the future. So let's add it here. Okay. So now this is done. So it looks like we have solved the case for an option that is nested inside future, but let's experiment a bit. So let's assume that we want to change the external effects. So let's assume that now the outer box won't be a future, it will be something different. The inner box is going to remain an option. So for the lack of a better example of a box, let's say that our external box would be a list now. So what I'm going to do now is do like a poor man's refactoring, and I'm just going to rename the futures here to lists. So every future in this selection becomes a list. Well, for sure, we can get rid of the execution context for now, because they are not required if you are mapping over a list. We don't need a thread pool for that, for sure. And now there are two surprises. The first surprise is that the implementation of map hasn't changed. So although we changed the external effect from a future to a list, which seem like totally unrelated, the implementation of map in our wrapper remains the same. The second surprise is that you can say almost the same thing about the flat map implementation, except for one thing, except for the knowledge how to wrap a pure value inside our external box. So previously our external box was the future, so we call future successful. Here our external box is a list. So the only thing that we are missing here, and this is the only thing that differs in the implementation of the flat map, is how to wrap a pure value inside the external box. So in case of list, it's going to just be list.apply. And actually, if in the previous example with future, if we used future apply, this the like poor man's refactoring would be enough, because it would have been enough just to rename it. But we use future successful in order not to allocate a thread pool for a thread for a pure value. So this leads us to a conclusion that if it works so smoothly for like if we exchange the external box, the external effect, and the changes required were very limited. So we may ask ourselves what happens if you want to generalize it even more. So if you want to generalize the external box even more. So let's try to do it. So I'm taking this implementation again, copy pasting this. And now our external box isn't going to be anything specific. So we are going to rename the list to some X. And now we have an option inside X. So of course, the first thing we are lacking here is what X actually is. So we need to add another type parameter here. And this is going to be a special type because it needs to be a higher kind of type or a type constructor, or in other words, something that you can wrap a value with. So it can be a string, for example, because string doesn't allow you to wrap a value inside it, but it can be a future, it can be a list. So it's a higher kind of type or a type constructor, which is denoted by the underscore here. Now, of course, we need to adjust all the types here. So we need to put X here, and here. And well, it doesn't compile for sure. So let's think why it doesn't compile. In the implementation of map, which is here, value.map doesn't compile because it doesn't exist. So previously, value was either a future or a list, which we knew how to do map on because this is built in, but we don't know how to do a map on an arbitrary value, on an arbitrary type. But it turns out that here is the place where type classes that exist, for example, in Katz effect come to the help, because it turns out that you can pass this knowledge how to do, for example, a map on any value, almost any value, as a dependency or as a context. So using the using keyword. So actually, we can say that we need to have an instance of some type class that is going to allow us to do a map operation of an arbitrary type. And this type class in Katz and in other libraries is called a functor. So what we are saying here is that we require a functor of X, an instance of a functor for X to be present in our context. So when map is called. And it turns out that a functor of X would allow us to do a map on any value of type X. So I'm going to duplicate this implementation so that you can see what the difference would be. So now what we need to do is we're going to take that functor, call the map on it. And as you can see, like here, you could see that map requires two values. Like first is the thing that we call map on, and then the function. So here with the functor, we also need to provide the value that we are going to map on. And we need to provide the function. So we write it a bit differently because we need to use the functor instance to call the map. But if you compare those two, this is pretty much the same. So we need the value, we need the map function, and this is how here we call map on the value. Here we provide the value as the first parameter to the map in a functor. So we solved the map using a functor, which is like a type class that denotes how to do a map on an arbitrary type. So perhaps there's a similar way to solve the issue with a flat map. And it turns out that there's another type class in Katz effect, for example, that is called flat map. That, well, as you might guess, allows you to do a flat map on an arbitrary type. So we would require an instance of a flat map for X here in the context. And here you already know what to do, because what we are doing here is taking the flat map for instance for X, calling flat map on the value, because we still need to pass the value, and the rest of the implementation remains the same. So there is one final problem that we need to solve here, and this is how do we wrap a value, any pure value like the none, for example, here, how do we wrap it in our type X? Because this is the one last bit of knowledge that we are missing here. We didn't know how to do a map. We didn't know how to do a flat map. Now we don't know how to wrap it. So it turns out that, of course, there's another type class that is going to help us with that, which is called applicative. So we require another type class instance here, which is an applicative of X. And then applicative of X has a pure method that does exactly what you want. So this lets you write an arbitrary value in your wrapper type. So in X here. So that's it. So that it compiles. We implemented it. So we can see if we are still able to replace the effect here. So now we are just going to use option inside X with A and with future as our effect, like the external box. And it still compiles. So we have a wrapper that takes two type parameters, and it can still be used in a for comprehension. And actually, we can simplify things a bit. because if we dive deeper into what the type classes, here I'm using cuts, are. So if you go into the implementation of a flat map and upper in the hierarchy, you can see that the flat map is actually also a functor. So if we go back to our implementation, it looks like we can just like take the flat map from here and put it like on a higher level. So we are just leaving the applicative here. We are putting the dependency on the flat map instance here. We don't need the functor here because a flat map is also a functor. So we can use fmx here to do the map operation. So now we have a dependency on the flat map and we have a dependency on the applicative. And now is the point when we arrived at the magical M word, which is the monad, because it turns out that if you combine the capabilities of a flat map and an applicative, this is actually what we call a monad. So instead of requiring an instance of a flat map for X, we can require a monad for X. Let's just rename it to MX. And it turns out that at that point, we actually don't need the applicative here, because we can use the monad instance, the MX, to do the pure. So a monad actually gives you the capabilities, and you can think of monads. Well, of course, you can think of monads as of monoids in the category of endofunctors, but this isn't very easy to understand. But you can also think of monads as a structure that you can use in a for-comprehension. In other words, that lets you chain operations where the next operation, next computation requires the value from the previous one. And also, and monads also, like a for-comprehension, behave in a fail-fast manner, which means that, for example, if the user was not found here, the rest of the computation would fail. So this is like short-circuiting or fail-fast, whatever you call it. And also, so a monad has a flat map capability, which allows you for chaining the operations, and it has the capability of wrapping a value inside the monad, so the pure operation. And actually, the map operation, which is here and is required for comprehension, map can be implemented in terms of flat map and pure. So actually, having a flat map and pure is enough to implement a monad for any type. Okay, so one last thing that we can do here is different styles of passing the dependency, because here we are using another arguments list with the using keyword. In Scala 2, it would be implicit here, so it would be an implicit parameter that's going to be used here. But there's a different way to do it with the same effect, which is called context bounds. Because we can, when we declare the X type here, we can put a colon and say that we require a monad. That colon monad, which says that we require a monad instance for X to be available in the scope. But now the thing is that we are no longer able to reference this value, because when we use the parameter list with using, we have the named implicit value. Here it's not here, so we need to like instantiate it for ourselves. I'm not saying this approach is better. I just want like to show you the options. So we can say that we want the private value of MX, and here we're using another keyword which is new in Scala 3, which is called summon, and we can say that we want an instance of a monad for X. So again, in Scala 2, this would be implicitly. So the context bound would be the same. So the syntax here is the same for the X colon monad. To get the implicit instance from scope, in Scala 3, you use summon. In Scala 2, you would use implicit. But when using cuts, for example, you can do even simpler. Just notice the case. Notice that this is like regular font here. But if I can do something like that, so I remove the summon and just leave the monad, this changes to italics, which means that this is actually calling an apply method on a monad. So it turns out that the implementations of a monad in cuts have an apply method that what it actually does, it actually gives you the implicit instance. So this code is in Scala 2, so you have the implicit keyword, and it gives you an instance. So this is exactly what we did manually. Which approach is better? Well, probably if it's like repeated, you can have it as a dependency here with the using keyword. But there are also other ways to get it from the context, either using summon or just using the apply methods from the type class descriptions. Okay, so to summarize what we did here, we wanted to be able to use a nested effect, so an option nested inside anything, to be used in a for-comprehension. So for that, we needed a structure that is capable of or suitable for comprehensions, which means that it needs a map and a flat map method. So we implemented one. This was the most general one for this. And we used a bit of type classes to let us, to give us the knowledge how to do map, how to do a flat map, and how to do pure or wrapping on any pure value without knowing the actual type. So we assume that this comes as a dependency, of course, as a dependency. Of course, this must be implemented somewhere, but we don't care. We just declare the dependency that this knowledge must be somewhere in the scope. And by doing this, we are able to implement this wrapper in a very generic way. So now the question is whether this is a perfect solution. Well, there's not everyone agrees that this is a good solution, because what you can see here is there is like plenty of allocations here. So for every wrap, for every map, for every flat map method, we create a new instance, which means a lot of memory allocations. You can argue that when you are on a JVM, so on a platform which has pretty good garbage collection, this shouldn't be an issue because the old values might be discarded. But for some people, this is an issue, and this is like one of the main discussions around monad transformers. The other thing is that we worked with an effect that is nested once, so we had an option inside the future, and if it was nested 3-4 times, this wouldn't look that nice. So we would no longer be able to write a for comprehension like that. So it seems like but on the other hand, like this level of nesting, so that you have some notion of asynchrony and some notion of either error or not, or either value existing or not, might be sufficient for most of the needs. In a real life scenario, you might put an either instead of an option inside this some kind of outer effect that denotes asynchrony. So for most cases, it seems enough. And one last thing. What you can notice here, actually, we are missing a return type here. So this is a public method that we are exposing somewhere, and a good practice when using monad transformers is actually not to use the monad transformers directly, not to return them in the API that you are exposing. Instead, you should actually return the normal value here. So the thing that is actually nested in the monad transformer. So we should call value here. And then return. Okay, it's not going to help me fix this, so I'm going to do it manually. So this is a future of optional company. So this is for the public API. And one last thing that I forgot to mention is that we haven't invented anything new, and this is what was my initial impression when I hit this problem myself, because the thing that we did here, our option inside X, actually exists in CATS, for example, and it's called option T. Option T is a monad transformer for an option. It has the type parameters reversed compared to my implementation. So the first thing that comes here is an effect, and then comes the actual value. So we have actually reinvented the wheel. I hope this helped you understand a bit what the wheel actually is, thanks to the fact that we reinvented it ourselves. Okay, and I think that's all I had. I have a tiny advertisement. It's great to be back on the conference here. There's another conference that you might have heard of. It's Scala, and it's happening again in 2023. The date is in March. The tickets are already there. The call for papers is already there. So I really invite you to join. And I think Agata asked me to remind that we don't really have time for questions now. So if you have any questions for me, you can either catch me later, or I will be on Discord. So I'm there as well. Thanks a lot for your attention.